Welcome to this deep dive, where we're going to pull back the curtain on the completely invisible world of wireless signals. We're going to uncover the hidden battles that your phone, your Wi-Fi, pretty much every wireless device you own fights every single moment just to get you a clear, reliable signal. This quote from Anais Nin really captures what we're trying to do here. We're going to demystify the pretty complex science that makes our connected world possible. But my hope is that by understanding it, we can appreciate the sheer magic and the incredible ingenuity behind it all even more. Okay, so here's how we're going to break this down. We've got 5 parts. We're going to start in a perfect, kind of idealized world, and then we're going to gradually add in the harsh realities of the real world, one by one. All right, let's just dive right in. First up, I want you to imagine the absolute perfect environment for a wireless signal. Okay, think of it like a pristine, soundproof laboratory. It's a place where communication is about as simple and predictable as it could possibly be. So, in the world of wireless engineering, this perfect place has a name. It's called an additive white Gaussian noise channel, or just AWGN for short. In this ideal world, the only thing our signal has to deal with is this super gentle, constant, and completely predictable background hiss. It's kind of the foundation of all communication theory. Now, to actually send information through this super quiet channel, our devices need to speak a language that the receiver on the other end can understand. And these languages, they're called digital modulation schemes. They're really just different ways of encoding all those ones and zeros onto a radio wave. And what's really fascinating here is the fundamental trade-off that this reveals. It's a trade-off that exists in every single wireless system. The simpler languages, something like BPSK, they're like speaking very, very slowly and clearly. They are incredibly robust, super easy to understand, even with that background hiss, but they're slow. They don't carry data very quickly. Then, on the other end of the spectrum, you have complex languages like 16QAM. These are incredibly fast, kind of like speed reading, but they're also way more fragile. The tiniest little bit of noise can just completely corrupt the message. So here's the key takeaway for this perfect world. In this lab, the solution to basically every problem is simple. If your signal is getting a little lost in that hiss, you shout louder. You increase your transmit power. As long as you're loud enough to be heard over that predictable, steady noise, your connection is going to be crystal clear. But as we all know from our own experience, the real world is nothing like a quiet lab. All right, now let's see what happens when we leave the safety of that laboratory. We are about to introduce the first, and honestly, by far the biggest villain in our story, a phenomenon that's known as fading. So, what is fading? It's what happens when your signal doesn't just travel in one nice straight line from the transmitter to your phone. Oh no, it bounces off of everything. Buildings, trees, cars, even people. All these multiple copies of the signal, these echoes, they all arrive at your phone at slightly different times. And here's the thing, sometimes they add up and make the signal stronger, but other times they cancel each other out, causing the signal to just almost completely disappear. This creates a completely different and way more difficult problem than that simple hiss we saw in the lab. See, the predictable hiss of AWGN, you can beat that with brute force, just more power. But fading? Fading is a chaotic, random, and just plain vicious opponent. When your signal enters one of these what they call deep fades, it's not just quiet, it's gone. And the price for fighting this is absolutely astronomical. I mean, shouting louder doesn't really work when the person you're talking to has suddenly gone completely deaf for a split second, right? To guarantee your message gets through even during the deepest of those fades, you can't just shout a little louder. You have to shout with an unbelievable amount of power. And this chart just brilliantly illustrates the staggering scale of this problem. To get a pretty standard level of quality, what engineers call a bit error rate of 10 to the minus 3, a simple BPSK signal in our perfect little lab needs about 8 decibels of signal-to-noise ratio, okay? But to get that same quality in a real-world fading channel, that signal suddenly needs 24 decibels. Now, that 16 dB difference, that's not a small gap. That represents a power increase of nearly 40 times. 40! That's 40 times the power just to overcome fading. This brutal reality, it forces engineers to completely change how they even think about designing a system. It's no longer about just maintaining some average level of quality. Nope. It's now about managing something called outage probability. The raw chance that your signal will drop into a deep fade and your call will drop, or your video will just freeze up entirely. It's a constant uphill battle to minimize the probability of total failure. So fading is our main villain. It's the big one. But it is not the only one. Let's add another layer of real-world complexity here. What happens when you or your surroundings aren't just standing perfectly still? Yeah, I mean, the simple act of walking down the street, let alone driving in a car or riding on a high-speed train, that introduces our second major villain, a phenomenon called Doppler spread, which is a nasty consequence of the Doppler effect. You've definitely experienced the Doppler effect with sound. You know, the pitch of an ambulance siren changing as it speeds past you. Well, the exact same thing happens to radio waves. When you or the transmitter are moving, the frequency of those waves gets all compressed or stretched out. And this causes the very precise frequency of our signal to get smeared out. It's like it gets blurred. And here is the truly insidious part of this whole problem. This smearing of the signal, this blurring of the data, it creates something that engineers absolutely dread, an irreducible error floor. So the crucial point to get here is that this is a problem that raw power cannot solve. Just think back to that analogy of trying to read a sign from a speeding car. If the letters are all blurry because of your speed, it doesn't matter how brightly that sign is lit, right? You simply cannot read it. It's exactly the same for your phone's receiver. Once that signal is too smeared by motion, cranking up the power does absolutely nothing to improve the quality. Errors are now guaranteed to happen. Okay, we have one final villain to introduce to our little party here. And this one is also a consequence of the fact that signals don't just travel in a straight line, they bounce off of everything. This is called inter-symbol interference, or just ISI. Because some copies of the signal take a longer, bounced path to your phone, they actually arrive later than the signal that took the direct path. What this means is that a delayed copy of the data bit, or symbol, that was sent a moment ago can arrive at the exact same time as the new symbol that's being sent right now. So let's just walk through this. A symbol, we'll call it symbol A, gets transmitted. One copy travels directly to your phone. Another copy bounces off a building, takes a longer path, so it arrives just a little bit later. Well, by the time that delayed copy of symbol A finally shows up, the transmitter has already sent the next piece of data, symbol B. So your poor receiver gets symbol B and the delayed echo of symbol A all mushed together. It can't tell where one ends and the other begins, and this leads to a whole cascade of errors. And just like Doppler spread, this creates another type of irreducible error floor. Okay, so let's just take a breath and recap. We've met the enemies that are constantly, relentlessly attacking our wireless signals every single moment of every single day. And if I'm being honest, the situation looks pretty bleak. We've seen how fading causes the signal to just randomly vanish, which requires these enormous amounts of power just to stay connected. We've seen how Doppler spread from motion smears the signal, creating errors that power can't fix. And we've seen how inter-symbol interference from all those signal echoes makes the data just bleed together, also creating errors that power can't fix. Which, of course, leads us to the big, obvious question. I mean, given this incredibly hostile environment, how is reliable wireless communication even possible? How in the world can we stream high-definition video to a phone while we're riding in a speeding train? Well, the answer doesn't lie in brute force. It lies in decades of brilliant, just incredibly clever engineering. Scientists have developed this entire arsenal of counterattacks. Things like diversity, which uses multiple antennas on the simple bet that a signal fade probably won't hit all of them at once. Or advanced coding, which is kind of like adding a clever spell check to the data so the receiver can just fix errors automatically. And finally, equalization, which is a bit like having noise-canceling headphones for your signal. It actively filters out the echoes to make the original message clear again. These incredible solutions, that's a whole story for another time. For today, I really hope we've succeeded in making the invisible world of wireless just a little more visible. If you enjoyed this deep dive, please consider subscribing to the channel and liking this explainer. And definitely let us know in the comments if you have any questions or what complex topic you'd like to see us break down next. Thanks for watching.